Hello, my name is Nabil Javrin. I work at the Berlin Institute of Health at the Charité University Hospital in Berlin, Germany. We have worked on positional encodings for medical images and have been motivated by the observation that commonly used positional encodings do not capture distance as one might expect. As an example, you can see in the figure below different 16 by 16 image patch grids, one for every positional encoding. Shown is the similarity to the central patch as indicated by the color. In the sinusoidal positional encoding on the left side, you can observe that the similarity is not decaying at the same rate in every direction. This misalignment of spatial inductive bias motivated us to develop a positional encoding that not only aligns with our expectations, but also tackles problems like image anisotropy or encoding positions in videos. Our proposed anisotropic Fourier feature positional encoding, or short AFPE, is a generalization of the previously proposed isotropic version and makes it much more adaptable to the underlying nature of the data. Finally, our proposed AFPE did outperform all other tested positional encodings in anisotropic settings and also in echocardiography videos. We also found that Fourier feature-based positional encodings capture high-level shape descriptors much more efficient than the commonly used positional encodings. This has the potential to improve performance in other shape-related neural networks. If this sounds interesting to you, I would be happy to meet you and to discuss this work.
Hello, this is the presentation of PSGMTR, a transformer-based approach for pulmonary segment segmentation using Gaussian mixture models at the ShapeMI workshop, MICCAI. Pulmonary segments are functional subunits of each lung lobe. Segmenting them from CT is challenging because boundaries are invisible and must be inferred from bronchi and arteries. We propose PSGMTR, a transformer-based framework that directly takes city images and generates class-wise GMM parameters to model spatial distributions. For GMM parameterized spatial distribution modeling, the parameters define the probability density functions of class-wise GMM. For each primitive, mu, phi, and lambda denote the center point, importance, weight, and effective area respectively. A candidate point y is assigned to the class with the highest PDF value. Next, I'll explain how PSGMTR regresses spatial parameters. The input city images are processed by a resonant backbone, and the fusion module aggregates features through unfolding and channel reduction. These features are encoded by a transformer and decoded into GMM parameters from class-wise primitive queries. Each query represents a primitive for a specific segment class. During decoding, it interacts through self-attention and incorporates image features via cross-attention. PSGMTR achieves competitive performance, recording the lowest average HD95 score. In our analysis, the use of GMM parameterized spatial distribution modeling enables both PSGMM and PSGMTR to produce smooth and coherent segmentation borders. PSGMTR achieves even smoother boundaries. Also, both models produce spatially coherent distributions with high confidence near centers and lower at boundaries. PSGMTR shows balanced confidence across classes, while PSGMM over-relies on a few classes. We observed that in PSGMTR, each class-wise primitive query shows spatial correspondence. For example, query A defines the boundary between RS2 and RS3, while query B is consistently near the center of RS2. That's all for our presentation. Thank you for listening.
Welcome, I'm Daniel, and today I will be presenting our work a unified pipeline for explainable gait analysis. Gait analysis using motion capture is commonly employed in clinical settings to aid diagnosis. However, challenges arise. For many neurological diseases, such as Parkinson's disease, early symptoms are often subtle, requiring extensive experience. Additionally, clinical capturing setups lack standardization. Some utilize markers placed across the entire body, while others focus only on the lower half, including force plates or even RGB videos. As a result, data from these varied setups can't be analyzed uniformly, and physicians have to rely heavily on their unique expertise with specific setups to detect these subtle symptoms. The goal is to address these challenges with our work. To achieve this, we introduce a pipeline consisting of 3 major components. In the first component, we unify the arbitrary data into a common system using a statistical shape model. This is applicable as long as the data can be used to pose the model. The unified data is then classified into healthy or sick in the second part. For that, we employ neural networks that first extract pose features and subsequently classify the features of an entire gait sequence. To enhance the clinical applicability of our approach, we add explainable AI as the last step of our pipeline. In this component, we use explainable AI methods to visualize the importance of the inputs and project the importance back onto the statistical shape model. During testing, we have discovered that our networks learn correlations resembling symptoms of Parkinson's disease, enhancing its diagnostic utility. For more detailed insights and results, I invite you to visit me at my poster. Thank you.
Dear researchers, this is an introduction video of our publication ShapeKit in the MICCAI 2025 conference and workshop ShapeMI from Johns Hopkins University. ShapeKit is a toolkit for medical image processing that allows researchers to correct segmentation errors from AI prediction. While AI-powered segmentation tools have advanced considerably, they often produce masks with anatomical inaccuracies or missing structures, leaving their liability in clinical and research applications. Therefore, we present ShapeKit, which is a fast shape processing toolkit for various organs, allows researchers and clinics to correct segmentation errors in AI-predicted masks without the need to further retrain the models. It can be seamlessly integrated into existing pipelines. The main advantages of ShapeKit is that it fixes errors efficiently from AI prediction, and it requires no further model training. Then, it is effective across various organs and datasets. The design of ShapeKit is a plug-in-and-play pipeline, as simple as playing Legos. To use ShapeKit, the first step is to identify the shape errors in medical image segmentation. Here, we present 5 common segmentation errors, that is, artifacts, false positives, redundant structures, fragmented structures, and left-right errors. The next step is that after identifying all these errors, choose the necessary ShapeKit modules. Here, ShapeKit provides 2 general module groups that contains general processing functions and organ-wise processing functions. The general processing functions are the functions that is valid for all the organs across the body, and the organ-wise processing functions is the ones that specifically for some organs. After having all these modules, the users can organize their own pipeline and integrate it into their own system. To evaluate the performance of ShapeKit, we present the results of the DSCC score after applying ShapeKit for multiple datasets as well as the visualizations. In the table, it shows that ShapeKit can improve the performance of the segmentation across multiple organs in a great scale. And from the visualization, we can see that after applying the ShapeKit, the errors, they are effectively corrected. In a word, ShapeKit is a very effective toolkit in medical image processing that allows researchers to correct segmentation errors from AI prediction without the further effort to retrain the model. And thanks for listening.
Our work, Posterior Shape Models Revisited, looks at issues during partial target reconstruction and proposes best practices. For this paper, we will mainly look at linear models. A mean shape is deformed using a linear basis of deformation fields. If such a model is conditioned on observations, we call it a posterior shape model. If the original alignment of the shape model is not consistent with the domain of the partial target, then there are issues during reconstruction. We distinguish two cases. One, where there is a model mismatch, then we call it target agnostic. Otherwise, we call it target specific. The right shows how a target specific model requires no further pose optimization to fit to a specific target. This greatly simplifies posterior inference. Here in the top row, we show the two model priors. Target agnostic and target specific models have different variance patterns. The bottom shows posterior shape models conditioned on a small target, here shown in green. Target specific models provide much better posteriors. Unfortunately, target-specific models are not always available. For example, when a pre-computed target-agnostic model is available, but original training data is not. Here our work aims also to provide a method to get target-specific models in such cases. For this, we propose a projection operator, which directly modifies the alignment of an existing shape model to an appropriate one for the target. The common rigid alignment is summarized into a projection operator, which can be built directly into a linear shape model. As such, our projection imitates target-specific models. The bottom shows the effects of such a projection operator. Here, the top row shows a synthetic femur reconstruction experiment. For all the tested inference methods, like NICP, Metropolis Hastings, and normalizing flows, target-specific models, and also our projection, perform better than target-agnostic models. They provide a higher accuracy reconstruction. Additionally, we showcase that our method works for more complicated applications, like a noisy skull reconstruction. Here, target-specific models provide more realistic variants. I'm looking forward to seeing you in person.
Hi, my name is Tiangen Zhang. I'm a PhD student at National Taiwan University, and today I'm going to present our work, Anatomically Focused Patches for Lightweight and Expandable Knee OA Grading. This project was conducted under the supervision of Professor Hervé Lombard at Polytechnique Montreal. Knee osteoarthritis is one of the most common joint disorders, affecting more than 650 million people worldwide. Its severity is usually assessed with the Kjellgren-Lorentz or KL grading system. The KL grading is time-consuming and subjective, which is why deep learning methods have been developed for automatic grading. Unfortunately, most existing approaches rely on coarse bounding box regions of the knee. Without anatomical guidance, these methods often struggle with both accuracy and explainability. To address this, we introduced a novel framework for knee OA grading centered on anatomically focused patches, a new improved representation designed to guide deep learning models with anatomical shapes. This approach consists of three integrated components. 1. A method for generating these focused patches from bone contours. 2. A multiple instance learning or MIL framework to aggregate features from these patches. And 3. A post hoc visualization technique to explain the decisions from our model. We show that feeding these patches into a lightweight CNN combined with an attention-based MIL framework significantly improves performance. Our method outperforms influential prior work that use heuristic patches and even separates larger models like ResNet 34, while using over 85 times fewer parameters. Just as importantly, our attention-based visualization produces sharp, clinically meaningful saliency maps. Unlike diffuse maps from earlier methods, our method clearly highlights osteophytes and joint space narrowing, which are features that radiologists relied on for KL grading. In summary, by combining anatomical guidance with MIL, our work delivers a lightweight, accurate, and explainable solution for automated knee osteoarthritis grading. Thank you very much for listening.
In this video, we wish to present our work, a statistical 3D stomach shape model for anatomical analysis. In this work, we developed the first 3D statistical shape model of the human stomach. Our goal was to capture the stomach anatomical variability across individuals and to provide a quantitative representation of the stomach morphology. The main challenges were the stomach height deformability and the lack of an existing dedicated statistical model. Our solution is composed of a two-stage approach: synthetic data generation, real clinical data refinement. Our methodology is composed of 3 steps. In the first step, we build a 3D canonical template mesh. The creation of the stomach mesh was diversified through various dimensional and geometrical variations. In the next step, we created a statistical shape model from a diverse stomach mesh collection, which served as the foundation for our PCA-based shape space that captured the model variation. Finally, we refine our model with real-world data by aligning and adapting it to a CT-derived meshes from an open-source dataset, ensuring clinical fidelity. Our results will be explained through a quantitative and qualitative analysis. We use the generalization, compactness, and specificity metrics to capture the fitting error, explain variance, and the average distance to nearest training shapes. A qualitative analysis shows the difference between the ground truth CT-extracted mesh and the predicted shape model, using color to indicate per vertex mesh to scan distance. For more details, visit our website. Thank you.
Hello, my name is Gaspar Podobnik, and I'll be presenting Anatomy Gen, generating anatomically plausible human phantoms at high resolution. I'd first like to acknowledge my co-authors, Nidi Balodi, Benjamin Kailin, Tomasz Wertowicz, and Matthias Umberet. So the motivation behind this work lies in virtual imaging trials in medicine, where you would usually start off with the human anatomy model, then proceed with synthetic image generation, and then you would have different downstream use cases. For example, you would use these synthetic images for augmenting your training set. The common denominator here is the need for accurate and diverse human anatomy phantoms that you need to create at scale, right, so that you get a large enough diversity. So here we propose Anatomy Gen, and let me first describe the basic idea. So we have organ-specific shape model. In our case, these are deep SDF models, where we encode the biological variability in organ shape by the organ latent vector, and then of course we have the deep SDF autodecoder, and we train these organ-specific shape models first to capture the organ variability. The other part is the post-estimation encoder. So this component basically glues everything together by learning the spatial distribution of all organ shape models. So we have an additional latent space here, and it captures the spatial distribution of the organs. Now to the results. So in this figure, we see a couple of phantoms. The phantom on the left-hand side and the phantom on the right-hand side are basically created from two training latent vectors. And the ones in between are created from the interpolated latent vectors. And what we can see is that the bladder on the left-hand side and the bladder on the right-hand side, so the shape of the bladder increases smoothly. The size increases smoothly. And we can see the similar things with some of the back muscles and with the position of other organs as well. So to better inspect the organ pose variability, we plotted the centroid of each organ with a dot. And here is the diagram showing the organ pose variability on the test set. And we see basically that the pose encoder does not always predict the same pose, but it captures the variability. We took a step further and created some synthetic CT images. So basically we employed the diffusion model created by NVIDIA, the MICCAI model, and we conditioned it using our phantom, in this case the middle phantom here. And what we can see that the CT images created with this approach, they look anatomically plausible, right? Which is a kind of high-level validation of our approach. And on another experiment was taking the phantom, which is basically a mesh description of the anatomy, and rasterizing it using two different resolutions. One low resolution and one high resolution. And then we created two synthetic images, and we see that the level of details in the high resolution image is much better compared to the low resolution, meaning that the ability to create phantoms at arbitrary resolution it's a nice property of our approach. So the take-home message is that this kind of approach allows us to create meshes at arbitrary high resolution. The latent space allows us to model the biological variability and the spatial distribution of the organs. And because everything is differentiable, right, we can end-to-end train it, meaning that no manual intervention is really needed. We only need the raw segmentations that can be either manual or automatically obtained to train this kind of model. With that, I would like to thank you for your attention.
Welcome to the template-based cortical surface reconstruction with minimal energy deformation, ShapeMI 2025 paper. I'm Patrick Malindo. In this paper, we talk about cortical surface reconstruction from magnetic resonance imagery, a field which has seen a lot of deep learning advances in recent times, where CSR can be performed within seconds, and it works by deforming anatomical templates, which are modeled as meshes. Up to now, these new methods do not actively ensure the consistency between training runs, so if you train them multiple times, you might get different outcomes, and they do not take into account the optimality of the deformation energy. This is why we introduce the minimal energy deformation, or MED loss, which regularizes the deformation trajectories, and as we can show in our experiments, it improves training consistency and reduces the required deformation energy. The overview of such a pipeline of CSR with deep learning today is as such that, as we can see on the left, we have a template and we have an MRI scan, and the deformation GNN is using the MRI scan to guide the deformation and deforms the template in many different steps into the predicted shape. What we add with the MED loss is a regularization on this deformation graph neural network, such that we get optimal trajectories and a better consistency. And we can also see that so far most losses, such as the chamfer loss, which were used for these methods, are computed between a predicted shape and the ground truth shape, while our MED loss acts between the template and the prediction. We incorporate the MED loss into a recent template deformation-based CSR method called V2C Flow, and from now we will call this V2C MED. We train both V2C Flow and V2C MED on the ICO 7 and ICO 6 mesh resolutions. For the consistency investigation, we train each setup 3 times, and we measure the consistency by the root mean square deviation, or RMSD, of the vertex positions between training runs. We also track the deformation magnitudes of each vertex to compute the deformation energy on a vertex level. The results, as we can see in this table here, show that the V2C MED, or the MED loss, produces predictions that are of comparable surface quality and accuracy as the V2C Flow baseline method. And we can see that the deformation energy itself has been significantly lowered, and the reproducibility has been significantly increased. So the quantitative data show that the MED loss is doing its job. We can also see this in the visualizations. Here we plot the vertex level deformation energies across the training set. On the left we have V2C Flow, on the right we have V2C MED. These energies have been projected and colorized onto the template meshes, and we can see a drastic improvement here. The same goes for the consistency between the 3 training runs. We can see that with a MED loss, each vertex ends up to be in a very similar neighborhood as in the other trainings, while without the MED loss, we have more variability between the vertex positions, which means the RMSD will be much higher. In conclusion, we demonstrate that the MED loss leads to consistent quantitative improvements in reproducibility and the deformation energy, while maintaining high reconstruction fidelity, and the consistent improvements across different mesh resolutions also suggest that the MED loss generalizes well. Thank you very much for your attention.
Today we will be presenting our work, Osteodeform, which is based on osteophyte-aware shape deformations of distal femur models for surgical planning and total knee arthroplasty. Assistance of 3D femur model has proven to be very useful for image-guided total knee arthroplasty, or TKA. Osteophytes are bony projections that occur at various joints. In our work, we will mainly be focusing on osteophytes occurring at the knee joint, that is, distal femoral osteophytes. The occurrence of these osteophytes alters anatomy, which in turn makes surgical planning inaccurate and difficult. We identified this as our problem statement. When we input an osteophytic distal femur 3D model osteodeform, the geometric learning framework that we are introducing removes osteophytes and outputs the healthy or pre-diseased distal femur 3D model. Due to the limited availability of 3D osteophytic femur models paired with their healthy counterparts, we also propose a synthetic osteophytic data generation pipeline and introduce the open source OST femur dataset, which you can view using the QR code present on the slide. It contains 495 unique models with paired correspondence. Our osteodeform has been evaluated on this dataset. The proposed architecture for osteodeform consists of the following sections: latent interpolation using radial basis function or RBF, the deformed points computation, and healthy femur prior retrieval. Uh, Latent interpolation using RBF takes as input control points sampled from the mean femur model, the osteophytic femur model, and randomly initialized latents. We deal with this interpolation in two levels of details: LOD1, which represents the global level of detail, and LOD10, which is for the local level. So LOD1 is, like I said, the global level of detail, which captures the overall details or the coarse details of the femur. LOD10 is the local one, which captures the finer details in the femur model. The RBF interpolation is done using Gaussian kernel. Here we are looking at the velocity field parameterization and deformed points computation. Each point on the osteophytic femur deforms over time via a neural ODE or an ordinary differential equation. We predict a velocity field using an MLP which takes as input the point location, the time, and interpolates the latent features. An ODE solver integrates this velocity field in order to transform the osteophytic femur into an osteophyte-free femur, and hence we get our output of the pre-deceased femur model. Here we are looking at how our deformation network is trained. So we minimize the chamfer distance between our deformed and the target femur surfaces. The gradients are computed using the adjoint sensitivity method, enabling efficient training of neural flows. Finally, we perform a surface reconstruction in order to get the 3D model of it. This is our validation loop where we solve one important problem that we've identified. So, in real world deployment, true healthy femur meshes are rarely available for fine tuning osteodeform. So, as a solution, we present the healthy femur prior retrieval or HFPR, which retrieves the closest healthy femur prior from a latent database instead of requiring the true ground truth meshes. So, this happens by training an autoencoder on osteophytic femurs and thus building a latent database. Now we encode query osteophytic femur to a latent vector and use cosine similarity to retrieve the most similar healthy femur latent code. This retrieved healthy femur is used as the deformation target and its latent codes are predicted via an LOD-PCA or level of detail principal component analysis to keep the deformations within the healthy femur distribution. So you might wonder why exactly we need this, and we will be looking at all of it in the results section.
The results section of osteodeform, which is a model trained to remove osteophytes. Osteophytes are bony projections commonly seen in osteoarthritis. Our dataset, which is the OST femur dataset, contains 495 osteophytic femur meshes. Out of these, 405 were used for training along with their corresponding healthy femurs. The aim is not just to remove osteophytes but to restore the femur shape while preserving anatomical accuracy, which is crucial for surgical planning in total knee arthroplasty. Osteodeform was trained for 200 epochs using Adam Optimizer. Each mesh was randomly sampled to 15,000 points. Training was done on an RTX 4090 GPU, taking about 20 hours for the full dataset. The model runs through iterated deformation, optimizing its parameters using chamfer distance as its loss. In this animation, we can see how osteodeform effectively removes osteophytes and deforms into a healthy femur shape
from an osteophytic femur input. To be seen in this section are the osteophyte quantification, effect of various levels of details, effect of various RBF kernels, and the significance of healthy femur prior retrieval or HFPR. Coming to the osteophyte quantification, to effectively quantify osteophytes, we have come for an osteophyte removal metric. Since standard shape metrics such as chamfer distance or dice scores don't effectively capture the osteophyte specific removal. In TKA planning, osteophytes burden is particularly in the condylar regions. So we define a convex hull of the healthy femur and identify points outside it as osteophytes. Using a distance threshold, we determine whether these points are removed from the osteodeform output. On the test set of 45 femurs, osteodeform effectively removes 70.7% of osteophytes on average. Clinically, removal of posterior and medial osteophytes is especially important for improving TKA outcomes and our model is effective in these regions. The red point cloud indicates the osteophytic distal femur. The blue point cloud indicates the osteodeforms output. And finally, the orange indicates the osteophytes which have been removed. In case 1, we are removing the marginal osteophytes as these are very prevalent in these regions, especially in the margins of the condylar region. Around 62.5% of osteophytes are removed. In case 2, we see that there is a removal of posterior osteophytes, which are particularly in this section. Around 98.7% of osteophytes have been removed. To better capture both global and local anatomical variations, we use levels of details or LODs. LOD1 capture broad global deformations, while higher LODs capture fine local adjustments. The best results come from combining LOD1 and LOD10, as you can see from the visualization, giving a good balance of accuracy and efficiency. We have also tested different radial basis function kernels, and the Gaussian kernel consistently outperformed others, giving the lowest errors in distance metrics. Coming to the significance of HFPR, we fine-tuned the model with an additional constraint called HFPR, healthy femur prior retrieval, which has already been briefed in the methodology section. Without HFPR, the model removes osteophytes but provides irregular and anatomically distorted structures. With HFPR, the osteophyte not only removes osteophytes but also preserves the anatomical contours. So we can see what happens with HFPR. The healthy femur prior is fetched from the latent database by HFPR. And this prior is actually very similar to the actual healthy counterpart of the input osteophyte femur. So this is needed as it will guide the deformation process and preserve the contours, which is quite visible in the regions of the coronal view, sagittal view, and the axial view. What happens without HFPR is that the deformation process does not happen effectively and the contours aren't preserved. So this deformation will take place without any boundary condition, and this visualization can be seen in the coronal, axial, and the sagittal views. And even in the mesh visualization, we can see how distorted the anatomy looks. For clinical validation, we conducted a femur morphometric analysis. This involves automated annotation of anatomical landmarks using alpaca, followed by computation of clinically relevant measurements. We evaluated 4 key morphometric distances, which is the medial lateral width, the medial and lateral condylar sizes, and the AP notch. Across 45 test femurs, the average morphometric error was only 0.022 with a mean and a standard deviation of 0.005 mm. showing that osteodeform maintains high anatomical accuracy. This method is especially strong in preserving anterior anatomical regions and crucial for surgical planning. So in the key observations, we can see in the FML, we have a very low median error and a tighter interquartile range. In the AP notch, the interquartile range is very narrow and has a very minimal variance. For the posterior metrics such as PDFFC and PDFLC, we have slightly higher medians but controlled variances. The future directions would include to validate results through cadaver studies, optimize the model for real-time surgical applications, expand the data set to include more diverse femur variations for better generalizability. Ultimately, this work contributes towards more precise, automated, and clinically useful surgical planning. Thank you for listening.
Our research. My name is Roman. I'm the first author of the paper we're presenting at MICCAI ShapeMI workshop. I work in the Eindhoven University of Technology, and the research is carried out in collaboration with Philips Healthcare. So the research we made is on shape compression for interventional device tracking. You can ask me what actually do we measure, what the data we work with. So it's medical data recorded during surgical interventions. Basically, it's shape of a catheter used for surgery. Measure its shape is possible with distributed acoustic sensing, which allows to really feel the shape of the device along its length. And this is the output of the system. It helps to navigate catheter inside the body. And compression is essential for this sort of data because during a couple of minutes of procedure, the system outputs gigabytes of data. You can imagine for surgery that lasts like 1 hour or longer, it would generate enormous amount of data that we need to store and we need to display. So compression is really essential here. And what is the main driver for compression normally? It's a representation of signal in a minimalistic form. So we do here. Instead of storing the whole data, the whole signal domain, which is more than 2K points for 3 coordinates, we store only few data points along the length, so-called knots, and those knots are used for in a spline fit model to reconstruct signal in between those knots, so we don't have to store everything. When it comes to spline knot approximation, it's essential the way you place those splines, because you can imagine not every section of the curve is equally important for compression. For example, highly curved areas are we expect more knots needed to be assigned for this area to effectively compress this shape, this section of the shape. So we developed, as a part of our solution, a compression solution, an adaptive knot placement algorithm. It's heuristic algorithm, so we use some feature extracted from the signal. Feature function in our case, it's power transformation of the curvature. So given shape, we extract this curvature and we apply a power transformation to it. Then we calculate cumulative feature function, so cumulative curvature, and considering that every knot interval must contain the same amount of geometric information, we subdivide the fiber length on those knot intervals. and it results in a nice spline fit. This approach allows to estimate near to optimal node placement. We prove it by comparing to other alternative node placement methods. Here on this figure, you can see that with our algorithm, we achieve the lowest reconstruction error. Our algorithm is shown in red, and the horizontal axis is subsampling rate. So basically, a number of points we retain from the overall signal domain. So with very few points, we can get away with nice compression. There are very few methods for shape compression presented in literature. Shape like our shape, like 2D or 3D signal. A method that we compare our the present algorithm is something that was developed in our group before. It's based on dimensionality reduction and smart subsampling. I refer you to this paper for more information. So the current approach we're presenting is actually outperforms this method as follows from this rate distortion curve. So you can see that current method lies, the curve of it lies below the curve of baseline approach. So providing lower error at the same compression rates. Also, it's important to bear in mind that we're interested in real-time compression because everything happens in real time during the surgery here. So we need to display the device within the body with minimal latency. And minimal latency for 50 shapes per second is 20 milliseconds. And this plot shows us the characteristics of compression rate vs time. So having more nodes, so lower compression, working somewhere here, we need more time to process the signal because we have more nodes to deal with, more nodes to build spline approximation. And vice versa, having fewer nodes, it gives us higher error, so it's a trade-off, but we're able to work in a real-time regime then. Therefore, we demonstrate a shape compression algorithm with heuristic node placement and spline fit of shapes. It achieves a state-of-the-art result for medical shapes recorded during invasive surgeries. Our current work is focused on improving the node placement because it's a hard combinatorial problem, so we can only estimate it. And now we're working on estimation schemes powered with some AI algorithms. Secondly, we are working on a temporal compression of shapes. And here our driver is eliminating redundancy in a time domain. Redundancy originates from the fact that the shapes following each other every 20 milliseconds, you can imagine they don't change that much every 20 milliseconds. So a lot of shapes just resemble each other. So there is a huge room for leveraging this redundancy, improving compression. And moreover, this method can be extended for another shape data. Somewhat similar approach with spline fit compression was demonstrated for multi-channel electrocardiogram signals. So we also intend to extend the results for the medical data set that can benefit from spline fit. In this regard, we're interested in collaboration with another groups, medical groups that have possessed data like this to include in common publication maybe. So if you're interested in collaboration or you have any questions, please find me. This is my LinkedIn link. Address me and I see you on the conference.
The paper, A Simple Modality-Agnostic Representation for Scoliosis Phenotyping, shows how a real-valued, low-dimensional Fourier sine series is used to model the shape of the spine. The midpoints of the segmentation mask are taken, and the curve is then rotated, transformed, and zero-bounded to make a sinusoidal geometric representation. The curve is then decomposed into its Fourier sine components using a discrete sine transform. The first 10 sine coefficients are taken and fed into a simple feed-forward neural network to classify the phenotypic characteristics of scoliosis. These are the presence of scoliosis, the number of curves, and the location and direction of the largest curve. A discrete sine transform, a form of Fourier analysis, is used to decompose the sine signal into its component parts. This produces a real-valued output, which is preferable to a discrete Fourier transform or fast Fourier transform, which have complex outputs. Each sine coefficient is a sine wave, and the original curve can either be fully or partially reconstructed by summing the sines together. In the paper, the curve is reconstructed using 10 components. Here, the first 5 sine components are summed to produce a partial reconstruction of the original curve. The simplified 10-number representation also makes it easier for the network to learn the correlations for phenotypic classification. The model was trained on representations from the Avon longitudinal study of parents and children's DEXA imaging cohort, but a held-out test set was kept for evaluation. We also evaluated on the 2019 MICCAI Automated Accurate Spinal Curvature Estimation dataset and the UK Biobank's imaging cohort of MRI scans. The MRI segmentation masks were projected from 3 dimensions to 2 dimensions. The same model is used to evaluate across all 3 datasets without fine-tuning. The method shows comparable results to Jamaluddin et al. 2018, where an image and segmentation classification network exhibited excellent performance on the DEXA modality. It's noteworthy that the network achieves comparable results whilst only having 18,000 parameters. Further, the direction and location of the largest curve can be predicted. Lastly, one model can classify on X-rays, DEXA, and MRI representations without fine-tuning. Thank you very much for listening. If you found the talk interesting, please read the paper, A Modality-Agnostic Representation for Scoliosis Phenotyping.
Hi, thanks for watching this video. I'll be presenting my paper, A Scalable Toolkit for Modeling 3D Surface-Based Brain Geometry today. Before jumping into the proposed toolkit, I would like to go over the benefits of shape analysis in subcortical brain. Volumetric analysis examines each structure by single measure matrix value. On the other hand, shape analysis gives you more details in different scene groups. This sensitivity to local subfield changes helps you to examine neural connections or brain functions related to the altered subfields in a neural condition. With this benefit, we proposed a Python-based toolkit in end-to-end workflow to support multi-site harmonization, fast vertex-wise statistical modeling, machine learning analysis, and result visualization. For shape analysis, we adapted Enigma standardized pipeline. In this pipeline, meshes are constructed for 7 subcortical structures using free surface segmentation and registered to Enigma template. The 2 vertex-wise measures are derived. Radial distance indicates the distance of each vertex to the medial curve and represents a measure of local thickness. Surface Jacobian estimates the Jacobian determinants to map average template to the surface of the subjects, and it represents the surface dilation ratio between the template and the subjects. In neuroimaging studies, naively combining multi-site data sets may add non-biological sources of variability to the data. Here, we adapted 2 commonly used harmonization techniques to adjust potential side effects. To expedite statistical analysis process, we integrated FEMA into our toolkit, and we obtained 16-fold faster computation. In this paper, we showcased our toolkit using Enigma bipolar disorder working group samples from 21 sites. We performed machine learning analysis using logistic regression with TV-L1 constraints. And we've been adding different models and interpretable weights map from the trained model. Our toolkit also supports interactive visualization. You can see more details by scanning this QR code. For next step, we plan to integrate cortical surface analysis protocol and add other machine learning and interpretable AI models. If you have any questions, feel free to contact us, and if you're interested in joining Enigma study, scan this QR code. Thank you.
Aloha mai kako, my name is Ariana Bunnell, and I'm a PhD student at the University of Hawaii at Manoa. Today, I'm going to be presenting our paper entitled Deep Learning Enables Large-Scale Shape and Appearance Modeling in Total Body DEXA Imaging. Total body DEXA imaging is a low-cost, low-radiation modality which can be used to monitor body composition and bone health. Total body DEXA has several imaging modes which we can extract based on X-ray attenuation values, including ratio, fat, and bone mineral density, as well as bone and lean tissue. In this work, we use data from 5 large NIH studies from across the lifespan: Health ABC, the multi-ethnic cohort, Mr. Oz, Shape Up Adults, and the Handles study. So traditionally, to do this kind of modeling, we need to hand label fiducial points on the images, which is very time-consuming and requires training. We use a subset of our data, around 1,600 scans, previously labeled by trained technicians, to train and validate a deep pose model to predict these 105 fiducial points shown here. And all of these points have precise anatomical definitions along the skeleton and skin boundary. We then use this trained model completely out of sample to predict fiducial points for 30,000 additional scans from the Mr. Oz, Handles, and Health ABC datasets. This model performs with 99.5% correct key points and 0.007 normalized endpoint error. From there, we resplit our data to discover our principal components for shape and texture. We then associate our discovered modes to biomarkers of interest by examining the tails of the distributions. For each feature in the SAM space, and for each health marker, we identify all images in the test dataset falling below the 10th and above the 90th percentile of the principal component in the training dataset. For each health marker, a 2-sample Kolmogorov-Smirnov test was performed. When testing for distributional differences using our KS tests, we find that metabolic markers like glucose, like you can see here, and fasted insulin were found to differ at the tails. Frailty markers were not found to be significantly different in general, but cardiometabolic markers were, with HDL cholesterol ratio and calcium among those showing statistically significant differences. So our method really opens up opportunities for doing more analysis and exploring principled predictive modeling of these markers on really huge databases of total body DEXA scans, which provide very detailed look into the body composition and bone health of an individual. The limitations of this work are a lack of consistent health markers and longitudinal data, which we hope to amend in future work with new data sets.
This work focuses on comparing the significance of changes in shape and physics of flow in the common iliac vein geometries of patients with deep vein thrombosis of the lower limb. Venous anatomy varies significantly between patients. Blood flow conditions are relevant for clot development and DVT treatment outcomes. The relative significance of shape and flow are investigated here. Anatomy comes from medical images collected in standard practice. Flow comes from simulations because it's not measured in the clinic. Statistical shape modeling was used to analyze the shape variability within a set of 24 2D vein projections. Some came from angiography images and some were artificially generated. Computational fluid dynamics was used to compute the area of wall shear stress covering the vein below 3 thresholds on 3D extrusions of the 2D shapes. This is an example result combining SSM and CFD. Each plot corresponds to a different wall shear threshold. 3 axes are the shape modes most correlated with this metric. Colors of the markers represent the wall shear area. Each marker is also labeled with shape ID. IDs are colored to group shape deformations. For example, labels of all stenosed vein shapes are highlighted in yellow. The shape modes that explain the most geometric variance are not necessarily the most influential for fluid dynamics. They also vary depending on the wall shear threshold. Ongoing work focuses on extending the shape set to more patient-specific geometries and performing shape analysis on a set of 3D shapes for comparison.
Hello, I'm Mathilde Monvoisin.
And I'm Louise Piécuche, and today we are here to talk about our work, which results from collaboration between several French institutes, in particular the LS2N and MIP Laboratory and University Hospital of Rennes and Nantes. Both first authors have worked equally on the method entitled Implicit Shape Prior for Few-Shot Assisted 3D Segmentation.
The clinical motivation for this work is to reduce clinicians' workload in complex 3D segmentation tasks with an interactive method. The first use case is radiotherapy planning, where accurate segmentation of organs at risk can minimize radiation exposure. And the second use case is diagnosis of age-related diseases like sarcopenia, where muscle mass and muscle shape quantification from 3D ultrasound can help with the diagnosis.
Implicit neural representation can encode population shape prior, just as in Amiranashvili et al. Work that we studied. In this work, Amiranashvili et al. Used an MLP to map 3D coordinates with a latent vector to predict class probabilities of a voxel. During the training phase, the parameters and the latent vector are both optimized in order to obtain a 3D volumetric shape from 2D slices during the inference phase.
In this baseline, the slice selection is to uniformly position the slices in the volume, which results in some cases missing important zones like the eyes, which are small organs, or missing the insertion of the muscle that are critical in the segmentation. This method is then suboptimal, which is why we propose an alternate shape slicing optimization. In the first case, we consider taking the middle slice of each organ and then iteratively add the slices that correspond to the highest error in the training set.
In the second use case, we also use the middle slice, but also add the insertion of the muscle as the minimum amount of slices selected, and we iteratively add the slices with the highest error from proximal and distal zone.
The quantitative results give, in most metrics, a better average and a better standard deviation that indicates improved performances and a more robust selection of the slices.
We also obtain qualitative results that show higher accuracy even with a minimal number of slices. If you are interested in more details about this method, feel free to contact us or to read the article.
My name is Tomáš Krsička and I'll present our work on benchmark-ready 3D anatomical shape classification. 3D anatomical shapes are often represented as meshes, which makes graph neural networks a great tool for modeling them. But there are two problems. First, there hasn't been a standard benchmark dataset for medical shape classification, which makes it hard to compare methods. Second, existing graph pooling methods either lose important structural details or are too slow for high-resolution medical meshes. We contribute two things in this work. First, we introduce MedShapeNet 19, A curated subset of MedShapeNet with 15,200 anatomical meshes across 19 balanced classes with predefined splits for training, validation, and testing. This makes it easy to reproducibly evaluate anatomical mesh classification tasks. Second, we propose pre-computed structure pooling or PS pooling. In contrast with other graph pooling methods, the node correspondences for PS pooling are pre-computed before training. They are derived from the internode distances between subsequent levels of simplified meshes. This brings a structural prior into the pooling operation while still performing the majority of computationally expensive tasks before the training phase. We integrated PS pooling into a self-supervised graph autoencoder and evaluated it on a downstream classification task. Models pre-trained with PS pooling show a significantly increased cluster density in the feature space. Additionally, our models reach fully supervised performance using up to 8 times fewer labeled samples. Even with less than 1% of the data labeled, our method still achieves over 70% accuracy. We look forward to discussing this with you at the poster session.